Hi everybody, welcome back. This is the fifth lecture video for this course. Today we're going to be doing more descriptive statistics. We're going to be discussing percentiles, a graph called the box and whisker plot, and the empirical rule. What we're looking at right here is stature for age and weight for age percentiles. And specifically, the group that we're targeting here are ages 2 to 20-year-old boys. So what you see is how a person's height, a boy's height, um, and projects to their future height as an adult. And it gives us a percentile of that child's height. So I want to show you here. Over here on where it says stature, we have the heights of boys. And let's look at an 8-year-old boy who is 49 inches. So to find that child, we have to look at the age 8 and the height 49 inches, which is halfway between 48 and 50. And we see where these 2 points meet, or these 2 values meet right here. And that is, we're going to trace that value up here. That is the 25th percentile. Okay. And if the child stays at the 25th percentile through their growing years, we can expect the child to be about 68 inches upon reaching age 20. Okay, so if we zoom in a little bit closer at the percentiles that are shown to us on this graph, they range from 5 all the way to 95. And for the child that we noted, the 8-year-old boy who is 49 inches tall, we traced that to the 25th percentile. Okay, the 25th percentile. Other percentiles that you see on the chart, 5, 10, 50, 75, 90, and 95. What we see with stature or height is that shorter boys have lower percentiles and taller boys have higher percentiles. And let's talk about exactly what a percentile means here. We see, using the chart, we see that an 8-year-old boy who is 49 inches tall is at the 25th percentile. So what this means is that that child, that 8-year-old boy who is 49 inches tall, is equal or taller than 25% of all other 8-year-old boys. So equal or taller than 25% of all other 8-year-old boys. We also can use the term percentile rank. We could say that 49 inches has a percentile rank of 25. Same thing as saying the boy is at the 25th percentile. Has the same interpretation in the sense that the child is at or taller than 25% of all other 8-year-old boys. So we want to make sure that when we're interpreting our percentiles, we distinguish between the data value, which is in inches in this case, 49, from the percentile rank. 49 is the height of the boy in inches, and 25 is the percent of other boys that have heights at or below 49 inches. Okay, 25% of the boys have heights at or below 49 inches. Percentiles help us determine a value's rank within its distribution. So a rank is where it's located within its distribution. 49 inches for this child, because this child is at the 25th percentile, if we think about percentiles as groupings that go from maybe like, let's look at it in terms of five, multiples of 5, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Let's keep going all the way up to 95. The rank of 49 inches at the 25th percentile is at the lower end of the distribution, whereas a person at the 95th percentile would be on the higher end of the distribution. Deciles are a way to divide our percentiles up into groups of 10. So decile divides a data set into 10 equal parts. Deciles are the points that cut the data into 10 intervals, each containing 10% of the data. So if you think of it in terms of percentiles, the first decile is the same as the 10th percentile, etc. here. So the 9th decile is the same as the 90th percentile. Okay, so it is important to recognize that if a problem uses the terminology for deciles, that you understand, for example, the 6th decile, you understand that the problem is referring to the 60th percentile. So if a boy's height is at the 9th decile, what it means is that the child's height is taller than 90% of the other boys in the distribution. So we're looking at taller heights on this side, shorter heights on this side. If we're thinking of scores on an exam, up here you'd have the higher scores on the exam, and down here the lower scores on the exam. We can also break up our distribution into 4 equal parts called quartiles. Each of those 4 parts contain 25% of the data. So if we do that, the percentiles and quartiles match up like this. The first quartile, we call it Q1, is also the same as the 25th percentile. And this is the value below which 25% of the data fall. So it means that if our distribution is represented by this number line here, this set of values that I'm highlighting in red represents 25% of the distribution. And then we have the first quartile. The second quartile, we call it Q2, is the same as the 50th percentile. And it's the midway point. Half of the data falls below and half of the data falls above Q2. Okay, half below and half above. This is the midway point. Q3, called the third quartile, is the same as the 75th percentile. And we have, notice that we have groupings of 25% between each of the quartiles. Okay. Quartiles help us visualize the spread of data and identify any outliers or skewness in the distribution. So here's an example that matches heights in centimeters to a percentile. These are some heights of a distribution of children living in a county in New York. What height or which height is the first decile? So since we know that deciles group our values, group our percentiles in groups of 10, we know that the first decile is the same as the 10th percentile. So we can see there that the 10th percentile height is 125. Okay, the 10th percentile height is 125. Which height is the median? So we weren't explicitly told how the median relates to percentiles, but we were told the definition of Q2. Q2 is the midway point that separates one half, the bottom half of data from the top half of the data. So knowing that the median is also the halfway point, we can say that the median is the same as Q2. And we know that Q2 is the 50th percentile. So the answer for which height is the median is 140. Which height has a percentile rank of 90? So we look at percentile 90, also known as the 9th decile. This is 160 centimeters. Let's keep going. Sure, sorry. Which is the percentile rank for a height of 130, and what quartile does that represent? So if we look at heights of 130, it looks like the percentile that represents is the 25th percentile, and we know that there's a mapping between the 25th percentile and the first quartile. So the answer here is Q1, the first quartile. What is the third quartile? Well, we know that's 75. So the answer to the question, what is it, is explicitly asking us what is its height, and its height is 150. So the answer here, 150. What height is the 6th decile? The 6th decile, also known as the 60th percentile. The 60th percentile has a height of 145. Okay, so that's how our deciles, quartiles, and percentiles map to these heights in this chart. So moving on to a visual example that demonstrates percentiles, deciles, and quartiles, we have the box and whisker plot. This is what a graph that is called a box and whisker plot looks like. It helps us visualize the quartiles in the distribution. So I misspoke. It's not about deciles, it's most about quartiles. The graph provides insight into the spread, center, and overall range of data. The plot shows 5 important numbers, and these are called the 5-number summary. The 5 numbers that the graph shows are noted here. We have 47, 51, 57, 63, and 66. These special numbers represent the following: the minimum data value. The next one here is the 25th percentile. This is Q1. Over here, this value in the center represents the median, also known as Q2, or the 50th percentile. Then the 63 represents the third quartile, the 75th percentile, and the very last number here, 66, represents the maximum. And altogether, these 5 numbers are called the 5-number summary of a data set. We can find the 5-number summary of any set of data, and we're going to be using our calculator to do this. Okay, on the TI-84, we're going to get started by putting numbers into a list. So using an empty list, you can pause the video and put these values into any empty list. I'm going to do it with you. So let me just get my calculator up. Okay, here I am with the calculator. I want to press Stat, edit, and I'm going to erase the data that's in L1 and L2 from our previous lecture. And I'm going to put in the 11 numbers from the slideshow into this list. So once the numbers are in, we're going to go back to the location that we set up the histogram from. That is second stat plot. And this is still set to view a histogram, so let's change it. With number 1 highlighted, make sure the other 2 are off. You're going to enter into number 1, make sure it's on, and under the type, you're going to choose the box and whisker plot, and it's the 5th one, the 5th graph. There's something that's called a modified box and whisker that's next to it. Don't choose that one. Choose this box and whisker plot right here. Under X list, highlight or type in second L1, where your data is. And then you can keep your frequency at 1, and if you like, you could change the color. I'm going to keep it at 9, at black. So we're going to now go to the zoom function on our calculator, which we haven't used yet. But if we use this zoom, it'll take us to, it'll give us an option number 9 here that lets us set the viewing window to match what our data for the box and whisker plot looks like. So we press enter on number 9. And I'm not seeing my box and whisker plot. So just a moment. Let's see what happened here. It's still set to histogram. Let's see what happened. I think maybe I did not quit this screen before I attempted to do zoom stat. So let's first quit this screen and then zoom number 9. Okay, and there's our box and whisker plot. If we press the trace key, it will show the cursor flashing in the center. That's the median. And at the bottom, it tells us that the median is 57. If we move to the left, it'll give us the minimum at the far left. That's 47. Q1, 51. The median, or Q2, is 57. Q3 is 63. And the maximum is 66. Okay, so that's how we create it. Let me just run through that again with you. In stat, edit, put your data in the list. Second, stat plot, change the plot type to a box and whisker plot. Make sure the X list is set to where your data is currently being listed, and then press or quit this screen and then press zoom number 9. And there you get your box and whisker plot. Hitting the trace key will allow you to see the values of the 5-number summary. So here's our completed box and whisker plot, and I added some labels to it so we could see what each of the values are. To interpret what we're looking at here, these pieces on the far right and far left are called the whiskers. Okay, the whiskers extend from the minimum to the first quartile on the left and from the third quartile to the maximum on the right. So in this case, our whiskers are noted here and here. The minimum is 47. The maximum is 66. And the whiskers show the overall range of the data. So if we calculate the range like we did with our discussion on measures of variability last lecture, we can do 66 minus 47 and get the overall range of our data. Okay, the box. So the name box and whisker is because there are two pieces. So box and whisker represent these two basic portions of this graph. The whiskers we just discussed, left and right, and the box is that rectangular piece in the center. Okay, the box represents the middle 50% of data stretching from Q1, the 25th percentile, to Q3, the 75th percentile. So in this example, the box extends from 51 to 63. The width of the box indicates the interquartile range, IQR, which is a spread of the middle 50% of data. The IQR is calculated by subtracting Q3 minus Q1. So take 63 minus 51, and our interquartile range is 12 inches. Okay. The median line goes through the center of the box. Sometimes it is positioned off center. Sometimes it'll be positioned here or here. In this case, it looks like it's right in the middle. It represents the 50th percentile, the middle value of the data. 57 inches is the median in this example. It means half of the weights are below 57 and half 57 inches and half are above 57 inches. The shape of the distribution. The position of the median inside the box as well as the length of the whiskers tell you if the distribution is skewed left, skewed right, or mostly symmetrical. So what you see here is when you do have a skewed distribution, for example, skewed left or skewed right, what you tend to have is the whisker on the left is dragged out further for skewed left distributions, and the whisker on the right is dragged out longer or further to the right for skewed right distributions. The position of the median is pulled in one direction. So notice that the median is pulled to the right, the whisker is pulled out to the left. The median is pulled to the left, and the whisker is pulled out to the right. And that's oftentimes what we see with skewed distributions. Mostly symmetrical distributions look just like that. They look mostly symmetrical. A lot of times you will see whiskers of equal length on left and right, and you'll see the median go pretty much through the center of the box. So let's compare these two box and whisker plots together. They do tell us something about variability. The length of the box and the length of the whiskers tell you about variability, and this is useful when comparing two box and whisker plots. We talked a lot about variability in the last lecture. We discussed what a big standard deviation does to a distribution and what a small standard deviation does to a distribution. What we're looking at here are two different graphs. So let's say this is the top, this one up here, and this one down here. One is more variable than the other. The longer whiskers indicate more spread in the data outside the central 50%. So we have a greater spread in the bottom box and whisker plot as compared to the top box and whisker plot, a greater spread. And in the case with the top one, we have shorter whiskers, which indicate that the data is more tightly clustered around the middle 50%. Remember, the middle 50% is the box. And when we have whiskers that stretch out away from that box, we have a bigger range outside the box. When the whiskers stay close to the box, we have more clustering of the values near the middle 50%. A wide box, remember that the width of the box was a measure called the interquartile range. A wide box suggests that the middle 50% of the data is more spread out, meaning more variability. So we do have that in the second example. We have a bigger box, a bigger interquartile range. We have more variability here. And the narrow box that we have in the top example, a smaller interquartile range, indicates that the middle 50% of the data is closer together, meaning less variability. And that's how we can examine the appearance of two box and whisker plots side by side and what they're telling us. So let's look at an example. We have 40 students, and these are the heights for the boys, and these are the heights for girls. And we have exactly 20 boys and 20 girls to make up the class of 40 students. We're going to create a box and whisker plot for both of those sets, and we're going to graph them together on our calculator, and we're going to state which box plot has the wider spread for the middle 50% of data. And what does that mean? What does it mean to have a larger interquartile range for one set of data in comparison to the other set of data? So we're going to get started by putting this into our calculator. We'll put the boys into L1 and the girls into L2. They have to be in two different lists in order to create two different graphs. So I'm going to flip to the calculator now and put in these numbers. So feel free to pause the recording, put in the numbers, and then fast forward through the rests until we get to the visual interpretation of the graphs. So we're going to press Stat, Edit. I'm going to clear out what we put in L1 before, and I'm going to put in the heights of the boys. Okay, those are the boys, and I'm going to go over to L2 and put in the heights of the girls. Okay, so I've got the heights of the girls in there. And now I'm going to graph these side by side. So to do this, let's go back to stat plot. And I only have one plot on right now, and it's graphing L1, where the boys' data is. I'm now going to put on plot number 2, so I could have them both on at the same time to plot where the girls' data is. So we hit on, going down to type, hit the box and whisker image, going down to X list, Let's do L2. And let's keep the color at some color that's different from the boys. So I'm going to keep it at the red that's given here by default. And I'm going to quit this screen. So now I have stat plot set so that, and I'll go back into it to show you here. Plot 1 is on and it's going to graph in black the boys' data from L1. Plot 2 is on and it's going to graph in red the girls' data from L2. And let me quit. And now to view it, we're going to do zoom number 9. Every time we have new data to graph, we have to recalibrate the calculator's window settings to view the data appropriately. So hit zoom stat number 9. Okay, and here are our side-by-side box and whisker plots. So what I like to do here is trace both graphs. So starting at the top with the boys, let's take note we have a minimum of 65. Q1 is 68, the median 70.5, Q3 74, and the maximum 77. Use your arrow down button to get to the girls graph here. Going through the numbers for the girls graph, the min is 61. Q1 is 63, median 65.5, Q3 67.5, and maximum is 69. So we were asked to calculate the interquartile ranges and interpret them. So to calculate the interquartile ranges, we have to calculate 74 minus 68 for the boys. And for the girls, we're going to calculate 67.5 minus 63. Let me just double check something. I was just double checking if the data on my calculator was all correct, and it is. So these are the numbers we're going to subtract for the interquartile range. 67.5 minus 63. That's going to give us a range or interquartile range of 4.5. And for the boys, we're going to subtract 74 minus 68. That's going to give us an interquartile range of 6. So 6 for the boys and 4.5 for the girls. So looking at our box and whisker plots side by side, we can see that the interquartile range for the boys is definitely bigger than that for the girls. So what does it mean? It means that there's more variability in the middle 50% of the boys' data set. We measured the interquartile range for boys at 6 and for girls at 4.5. So this 6, the difference, IQR equals 6, as compared to the girls, IQR equals 4.5, indicates more variability with the middle 50% for the boys' data set. Okay, we're going to move away from the box and whisker plot for the rest of this lecture and discuss a topic regarding the shapes of distributions. This is an example of a distribution of blood pressures, and we see blood pressure measured on the horizontal axis. We have 1, 2, 3, 4, 5, 6, 7. You can't see it there, but there is one box there. There's 8 classes in this or dividing up this distribution. And the size of each class is 12.5 in this example. And I've not created classes with you that take on these decimal quantities, but it is possible. And in this case, that's what we have. We have classes of size 12.5. The histogram here has the variable systolic blood pressure on the x-axis and the number of patients on the y-axis. So you know that the bigger the rectangle, the more frequent that particular class value is. So it's more frequent to have blood pressures here in the center than it is to have blood pressures down here or up here. Most of the patients fall in the middle range, from about 120 to 130. And fewer patients have very low or very high blood pressures, and we note that by the heights of these bars. This is a symmetrical distribution, and we did talk about the shape of distributions, but we're going to now take it a little step further. So imagine that you take that symmetrical distribution of 8 classes and you create even more classes. What happens if your classes get more frequent? So you have 20 classes instead of 8 classes. And so the width of your classes now have decreased in size. The width of each class is 5 mmHg. So you don't have the same big span of values for each class. The class sizes are now small. So what happens visually? The rectangles appear smaller as well. They appear more narrow. They've not changed their height though. You still have rectangles that go up high and some that are really short. So that's not what has changed. What has changed is the width of these rectangles, the width of these bars. Again, most patients fall in the middle range from 120 to 130, and fewer patients, again, have blood pressures on the very low end or the very high end. Okay. So again, we have most in the center over here, and we have few on the low end and few on the high end. It's still a symmetric distribution. It still is symmetrical with the bulk of the data in the center and tailing off on the left and the right. Now imagine we do that even more. Imagine we decrease our class width even more. So our classes are now much more narrower, and we have 50 classes now where we're grouping our data. Instead of 8, which then became 20, we now have 50 classes, and the width of each of those 50 classes is just 2. So again, we see our rectangles shrink in size, and so what we have are more rectangles in our picture, but the same pattern emerges. We have the bulk of our data in the center, most patients falling around 120 to 130, okay, with very few on the low end and very few on the high end. Still a symmetrical distribution. Now, what I just drew on top of this is that classic bell curve. This symmetrical distribution takes on the appearance of a bell-shaped curve. And that's exactly where the curve comes from. When we shrink those rectangles, those bars, down further and further and further till practically they're not even bars anymore, but just single points, the graph becomes a very continuous smooth line, and that is the bell curve. So if we trace along the tops of the rectangles, we see a bell-shaped curve appear. We call this distribution a bell-shaped or normal distribution. And it's normal because we tend to see this in a lot of real-world phenomena. We see a lot of things modeled by this bell-shaped distribution, where the normal or the most common tends to be in the center, and the rare is on the far left or the far right. When we have these normal bell-shaped distributions in our real world, the very center is always the position of the mean. Now, if we're dealing with a population, we label the mean or the middle of the bell-shaped curve, we label it with mu. And if we're dealing with a sample, we'll label the middle of the distribution with the sample mean x bar. For a population that is normal or bell-shaped, the center is always in The center of the distribution is always the location of the mean by mu for a population or for a sample X bar. Okay. Just as in the histogram, the variable being measured is placed on the horizontal axis of the bell curve. For example, blood pressure or cholesterol. So we would label our variable underneath our bell curve. Values below the mean are to the left of center. So if you think about the center as this notch right here, these numbers on the horizontal axis are below the mean, and these numbers on the horizontal axis are above the mean. Okay, below the mean and above the mean. The further away you get from the center, the bigger the difference from the mean. So a value, I'm going to call it X, to the left of center over here has a difference denoted by this horizontal line I'm drawing, but a value over here, X, has a difference noted by this horizontal line. The further away you get, the bigger the difference from the mean. And that is an important concept because if the mean is average or typical, the closer values are also a little bit more typical, and the values that are further away are more rare or atypical. Okay, so for example, if we're talking about blood pressures in a distribution, the center, the average blood pressure, values around the center are typical. It's more rare to see something that's on the very high end of the distribution on the far right. Those are very high blood pressures, and it's also just as rare to see something on the very left side, the very low side of the distribution, very low blood pressures. Let's do an example where we're measuring gait speed. An example of a normal distribution is gait speed. This is the walking speed in older adults. Gait speed is used to assess functional mobility and predict outcomes like fall risk or the need for rehabilitation. Research shows that gait speed in healthy older adults tends to follow a normal distribution. So this means that the average gait speed is in the center of the bell curve, and we have some people that have a gait speed that's very high, and that would be on this side of the bell curve, on the right side. And we have some people with gait speed that are very low, and that would be on this side of the bell curve. So the center, the average, denoted here by mu, is 1.2 meters per second. And that's here, 1.2 meters per second. And the standard deviation is 0.2 meters per second. Okay, so this is going to be coming in handy in a moment. The standard deviation is going to be necessary when we start thinking about the spread of this distribution. Okay, gait speed is meters per second. So these, the population that we're talking about are older adults. So this is not for the entire population, but for a select group of the population. Slow gait speed on the left and fast gait speed on the right. Okay, so we already noted that the mean was 1.2 meters per second, and we have a standard deviation, but we haven't done anything with it yet. What we're going to do now is think about one standard deviation above the mean. What does that mean to be one standard deviation above the mean? A gait speed that's one standard deviation above the mean is higher than the mean. So if the mean is 1.2, A standard deviation above that would be on its right. Okay, and exactly it would be 0.2 on its right. So to get that one standard deviation above the mean, we add 0.2 to the mean. Okay, so we're going to take our mean of 1.2 that's given to us here, and we're going to add a standard deviation that's given to us here. That's one standard deviation above the mean, and that happens to be 1.4. Okay, and that kind of makes sense because this horizontal axis is a number line. If 1.2 is in the center, to its right has to be a bigger number, and 1.4 makes sense. Okay, 1.4 meters per second. What gate speed is 2 standard deviations above the mean? Well, again, if one standard deviation above the mean was 0.2 more than the mean, 2 standard deviations above the mean has to be even more than that. So if we add a second standard deviation to 1.4, we get 2 standard deviations above the mean. Okay, so starting with the mean, adding 2 times the number of standard deviations, or 2 times the size of the standard deviation, 2 times 0.2, and that gives us 1.6. And that takes us a little bit further above the mean. So we have 1.2 is the mean, add 0.2 and we get 1.4, add another 0.2 and we get 1.6. That is 2 standard deviations above the mean. 3 standard deviations above the mean is going to take us almost off this graph entirely, but let's do it. 3 standard deviations above the mean, one more standard deviation past 1.6. Let's add another. So we have 1.2, the number of standard deviations, the size of the population mean. And then we're doing 3 times the number of standard deviations, 3 times 0.2, and we get 1.8. Okay, so we can also think of that 1.8 as 0.2 more than 1.6. So start in the center with 1.2, add a standard deviation, get 1.4, add another standard deviation, get 1.6, and add another standard deviation, get 1.8. We've just added 1, 2, 3 standard deviations above the mean. And by the by the shape of this bell-shaped distribution, we can see something happening. The further standard deviations we go higher away from the mean, the more rare that gate speed is because the graph is low at that point. So these are the very high gate speeds. These are the older adults that walk very fast, and it's rare. That's 3 standard deviations above the mean. That is not common. And let's look at the other side. 1 standard deviation below the mean. Now we're going to be looking at the group that is lower than average. 1 standard deviation below the mean is less than 1.2. So to get this number, we're going to subtract 1.2 minus a standard deviation, 0.2. And we get 1. Okay, 1 meter per second. That's 1 standard deviation below the mean. Let's look at 2 standard deviations below the mean. Let's take our mean and subtract 2 standard deviations. And I'm getting 0.8 now. 1.2 minus 2 times 0.2 is 0.8. So basically what I'm doing between here and here is I'm subtracting a standard deviation, 0.2. And then the next one to 0.8, I'm subtracting another standard deviation, another 0.2. And let's do it another time. Let's get 3 standard deviations below the mean. Let's subtract another standard deviation from 0.8, and that gives us 0.6. So to start, I had to begin in the middle with the mean. And on the right-hand side, I added a standard deviation, added a standard deviation, added a standard deviation, and I subtracted a standard deviation 3 times on the left. Okay, and this gives us a spread of gait speeds across the whole bell curve. The empirical rule is a rule that we're going to apply to this bell curve. It gives us approximate percentages for specific segments of any normal distribution. So we could be talking about gait speeds, or we could be talking about blood pressures or cholesterol levels or heights. But this rule applies across the board to anything that's normally distributed. So what it means is that we have a rule. It has 3 parts, and it tells us percentages um, percentages for each standard deviation away from the mean. Starting with the center 1.2, we first calculated 1 standard deviation above that. If we look at 1 standard deviation below the mean, it's 1.0. So between 1.0 and 1.4 meters per second, we have this range, or this segment of the population, and the rule tells us that about 68% of this population fall within this range. And this is true for any normal distribution. About 68% fall within the range of 1 standard deviation below, 1 SD below, to 1 SD, 1 standard deviation above the mean. So we could be talking about blood pressure. We could be talking about IQ score. 68% of the population are within that range. Okay. So in this example, 68% of healthy older adults have gait speeds between 1.0 and 1.4 meters per second. So you're going to remember for the empirical rule, 68% for 1 standard deviation below the mean to 1 standard deviation above the mean. That is within 1 standard deviation of the mean. Let's take this distribution and look a little bit further out to the right and left. So let's look a little bit for, oh wait, no, I'm sorry. Let's do this first. Taking that center 68%, people in this range are considered to have normal functional walking speed for older adults. So this middle group, this 68%, are good. They are good walkers. We can split the distribution in half here because 68%, or rather the bell curve, is symmetrical. So the middle 68% can be cut down the center with 34% on each side to sum up to 68%. So we have about 34% in the standard deviation below the mean, and we have about 34% in the standard deviation above the mean. Okay, and we have this across the board in any normal distribution. Okay, approximately 34 of the distribution falls between 1 standard deviation below the mean, and approximately 34% of the distribution falls between the mean and 1 standard deviation above the mean. So if we take it out a little bit further now, like we had done earlier, we're going to go out 2 standard deviations above the mean and 2 standard deviations below the mean. This is a larger group of people because now we're capturing the more faster walkers and even slower walkers. This is a bigger group of the population. The rule here, according to the empirical rule, which is true for all normal distributions, we can capture about 95% of the distribution within 2 standard deviations of the mean. So within 2 standard deviations of the mean is interpreted as 2 below to 2 above. Okay, 1, 2 below to 1, 2 above. And that's 95% of the distribution. That is a big piece of a population of a very large sample, perhaps. But this is a large segment. So we capture almost everybody in this range. So approximately 95% of healthy older adults have gait speeds between 0.8 over here and 1.6 over here. So from 2 standard deviations below to 2 standard deviations above, the rule says we have about 95% of our distribution in that range. Okay, again, now if we think that this bell curve remember that the bell curve is symmetrical, so if we have 95% between here and here, let's figure out what percentage go in these two pieces. Well, if the center was 68, let's figure out what's in both of these pieces and then divide by 2, and we could get what's in each question mark. So to get what's in both of the pieces, let's take 95 minus 68. That's going to give us what's in here and here combined. Okay, and that's 27. If we divide 27 in half, we have 13.5. So that gives a 13.5% in this segment and 13.5% in this segment. So we can break down our 95% into these pieces, 13.5 and 34 and 34 and 13.5. If we add them all up, that's 95%. Okay, a gait speed below 0.8 might indicate significant mobility issues. These are much slower people down here, okay? Potentially requiring interventions like physical therapy. A gait speed above 1.6 is high for older adults and may be a sign of excellent physical fitness. So that's what we see up here. Okay, so if we go even further to the right, if we go 2 standard deviations away is 0.8, 3 standard deviations away on the left is 0.6, and then 2 standard deviations above was 1.6, and 3 standard deviations above is 1.8. When we think about this big range, we capture almost all of the distribution in this case. Okay. According to the empirical rule, approximately 99.7% of the distribution falls within 3 standard deviations of the mean. So from 1, 2, 3 standard deviations below the mean, all the way to 1, 2, 3 standard deviations above the mean, we capture almost all of the distribution, almost all of the people in the distribution. Okay, in terms of gait speed, approximately 99% of healthy older adults have gait speeds between 0.6 and 1.8 meters per second. Now, why not 100% of the distribution? It's because we always have the potential for an outlier that could potentially be even slower than 0.6 or even faster than 1.8 that we account for outside of these vertical lines. So further on the right of this vertical line and further on the left of this vertical line, we potentially could have slower or faster walking people. Okay, and that's extremely rare. 0.3% fall outside this range. Those are extremely rare, and they would be considered outliers. Okay, so the 99.7% from 3 standard deviations below to 3 standard deviations above, and we break that down with the 13.5, 34, 34, and 13.5. We can calculate percentages between here and here. So what percentage are we talking about between here and here? Okay, so if we think about this piece, this is 95%. If we subtract 97.5 minus 95%, we'll get the sum of these two pieces. That's 4.7%. And if we divide that in half, that gives us 2.35 on each piece. 2.35 here and 2.35 here. Okay, so our breakdown for the empirical rule give us these 6 percentages that we want to remember and apply on problems that ask us about the empirical rule. So 2.35% of the population have gait speeds between 0.6 and 0.8, and 2.35% have gait speeds between 1.6 and 1.8. Summary of the empirical rule. Let's sum this all up, what we just calculated here. 68% of older adults have gait speeds within 1 standard deviation. That is from 1 meter per second to 1.4 meters per second. That's considered to be normal for functioning adults. And 95% have gait speeds between 0.8 and 1.6. This is mostly functional, but those below 1.0, this group right here, may need some attention. And 99.7% fall between 0.6 and 1.8. And anything below 0.8 right here, this group for sure requires physical therapy intervention, while those above 1.6 up here are considered exceptional. Okay, so that's how we interpret the empirical rule, and that sums up the end of this lecture. In your homework, you'll have to do something similar. You'll have probably a different application and not necessarily a gait speed application, but nonetheless, you still apply the empirical rule in the same way. You still have 34 and 34 in the middle, 68%. And then you have 13.5 and 13.5 separating out or going out to the 95%. That's 2 standard deviations below to 2 standard deviations above, and 2.35 and 2.35 from 3 standard deviations below to 3 standard deviations above. We see this over and over again with lots of phenomena in our real world that are mapped by the normal distribution. And so you can answer any question about a normal distribution knowing these empirical rule percentages. So I hope this was helpful. If you have questions, please reach out, and I will see you at the next lecture.